So today we'll be looking at T distributions, T tests. Then tomorrow we'll look at the non-parametric counterparts. And next tomorrow we'll look at calculation of sample size using WINPEPI. Historical background. In 1908, William Seeley Gosset was an Englishman publishing under the pseudonym Student, developed the t-test and t-distribution. So he was publishing his paper. This man was working in Harlan. Yes, is it Harlan? One of the, is it Harlan? I think it's in Harlan. So he was working there, and in Guinness, he was actually working in Guinness. And because you could not publish data from the company without permission, even if he requested for permission, I've given him. So he was publishing under the synonym Student. So we publish and put his name Student, because we will not put his own name. Because if he has put his name, they will have sacked him, because he had to publish under supervision, and he knew that they would not even permit him to publish most of the data. He was in love with statistics. So he was the one that discovered that when the sample size is very small, the Z distribution or Z test they were using, but I will not be able to actually compare small samples. So he was the one that invented or maybe discovered the T distribution. Gosset worked at the Guinness Brewery in Dublin. Yes, in Dublin. And yes, Dublin is the capital of Ireland. He found that existing statistical techniques using large samples were not useful to reduce the volume for the small samples that he encountered in his work. Simply the T distribution we are talking about, student T distribution, or you call it T distribution. Simply distribution of the T value when the sample consists of independent, identically distributed observations from a normally distributed population. What this one is talking about is that when you have two groups that are normally distributed, so you are trying to look at the difference between them. That difference follow a distribution. That is, if you sample two population or two groups, you are having two samples at the same time, and that parameter you are studying is normally distributed, and you are looking at a difference. The difference between them follow a pattern. So it's a family distribution, and it's a continuous probability distribution. When we are saying something is a family distribution, it's not like standard normal distribution that is just one. Standard normal distribution is just one. It's universal. But whenever you say a distribution is family distribution, it means that a different type based on the degree of freedom. We're going to talk about it. So it's a continuous probability distribution. For those of us that have watched a video on probability distribution in the previous lecture, a continuous probability distribution is a distribution of variable that you cannot actually know all the possible value of the variable. A variable that you cannot know all the possible value of follow continuous distribution, in the sense that if you cannot know all the possible value, there's no way you can calculate all the value, all the possible value, probability of the possible value. So for a variable that you know all the possible value, you can list all the possible value and list their probability. And that is what you usually do when you do your research. Like now, if you do your study in Nigeria now, there's a variable, geopolitical zone. We all know that we have 6 geopolitical zones in the country. So all you need to know that the people you are studying, how many come from south, how many from southeast, southwest, south, northwest, north center, northeast. Just know and now divide by the total for you to get the for a probability percent. That percentage is the probability of individual coming from each of this region. Because geopolitical zone we know all the possible value that it can only be one of the six. So you can know the probability distribution by just doing the study in the population. You'll be able to. If by the time we look at our census now, we know the distribution of each region. We know the population of each geopolitical zone. When you now put the population of each zone over the total Nigeria population, it gives you the probability of somebody coming from each region. So you see, because you know all the possible value is a form of discrete probability. The table that shows the percentage like that is a discrete probability distribution because it has given us all the possible value of that variable and their probabilities. The same thing tossing a coin. You know, it's head or tail, or anything that you know the different the category, male and female. You want to know what is the probability of a male or somebody shows now as a male in a particular place. It's just for you to know the population of male over total population of female over total. You should be able to know. So every categorical variable follow this probability distribution, but continuous variable like let's say age, blood sugar. There are infinite number of possible blood sugar. You cannot say that because if you say somebody is between 60 and 65 blood sugar, 60.001, 60.002, 60.009, infinite number even between two given numbers. So there are infinite number of possible value for a continuous variable. Because of that, since you cannot even know all the possible value, there's no way you can calculate the probability of all the, you cannot know the probabilities, you cannot calculate the probability of all the possible value because it's not possible. So it is not possible for you to have a table of probability distribution for continuous probability distribution. For anything that follow continuous probability distribution, like normal distribution, this chi-square distribution, F distribution, all those are continuous probability distribution because it's not possible. What you can do is to draw a graph. I think I will explain that one further when we get down. You can show it using a graph. We call it graph that show probability distribution is called probability density function. Now, it's a family distribution. We'll talk about it because it depends on the degree of freedom. As the number of degree of freedom increases, the T distribution approaches normal distribution. You're going to see that. Used for estimating the mean of normally distributed population in situation where sample size is very. That was why Gosset invented it when the population standard deviation is known. So these 2 points, we are going to revisit these 2 points. Let's look closely at the picture to understand the distribution, because most of the time talking to the head may not help. It's better you're able to conceptualize by using diagram, picture, knowing that brain record information in picture. Brain does not record information in number or letter, it's in picture. The probability density function is symmetry. When you say something is symmetry, is one side is mirror image of the other. It's bear shape, just like. So it has some characteristics that resemble normal distribution because normal distribution is bear shape. One side mirror image of the other. Now, probability, Dr. Afolabi, welcome. The probability density function is symmetry. It overall shape resembles the best shape of normally distributed variable with mean 0 and variance 1, except that it's a bit lower and wider. So it's like normal distribution in the sense that it's bell shape. But look at the red, is normal distribution. Can you see? The blue also is symmetrical, but you see it's flatter. The funnest thing that the area under the two graph is the same, is one. But it's just like we have a rope now. You can, or you have something that is plastic, you can bend. So you can, adjust the shape. So when it goes up, the degree of freedom goes up, which depends on the sample size now. As it's increasing, the thing will be bending up like the resembling normal distribution. Of course, the base will be narrow. If you look at it, it has a wider base. The blue has a wider base, but it's not as tall as the red. The red is the standard normal distribution, while the blue is T distribution. So the red is taller, but has narrower base, while the blue, which is the T distribution, is not as tall as the red, but has a wider base. So if you look at it, the area under the same. So as the degree of freedom increases, the shape of the T distribution begin to resemble normal distribution. Look at this first one now. Look at this one. Look at the graph here. You notice that, look at T distribution when the degree of freedom is infinity. That is, it has approached, because the standard normal distribution, the degree of freedom is infinity. So look at this tall one now, the standard normal distribution, and a T distribution that the sample size has increased drastically. It will approximate normal distribution. Look at T distribution with degree of freedom 20. Look at T distribution with degree of freedom 10. Can you see? So the lower the degree of freedom, the flatter the graph and the wider the base. But if you look at all these different graphs, 1, 2, 3, the area under each of them is the same area, but the flatness and the tallness vary, depends on the degree of freedom. So the standard normal distribution has a height and width. So and it's one, it doesn't change. But it's still distribution when it approximates normal distribution. As the sample size increases, the degree of freedom increases, it will look like the normal distribution. This one is still showing the same thing. Let's say this grid blue is the T distribution. This purple is the T distribution. The blue, maybe it's the blue or green. The one is Z distribution, Z distribution. The purple is the T distribution. You will see, look at the base now. Look at, the zero origin. The zero is in the middle. And if you remember, the 95% of the graph is in between minus 1.96 and plus 1.96 standard deviation. Minus 1.96 plus 1.96 standard deviation. Now, you will see that the blue aspect, 95%, 1.96 minus then plus 1.96, but for the 95% for T distribution, the area is between minus 2.201 and plus 2.201. No, we've already said it has a wider base. That's for the T that has degree of freedom 12. As the degree of freedom increases, what will happen? It will shrink back. That 95% middle will begin to approximate 1.96. That is one thing. So as the degree of it begins to go up, and the base is becoming narrow gradually until it goes that middle 95% area. When we talk about that, is the area of the graph. No, there's something here you need to conceptualize. You just need to, the statistics was developed by people, intelligent people that thinkers. So you just think, conceptualize. You know, we have already said that for probability distribution, continuous probability distribution, where Z is Z distribution, T distribution, chi square, Z distribution, F distribution are. You cannot have a list of table. You cannot have a table that shows the list of possible value, because it's not possible for you to have a list that these are the probability of different value, because you cannot know all the possible value. So you only draw graph. You can only show a graph. And intelligent people came and they discovered the solution by discovering normal distribution. When you get normal distribution, you know, just like somebody give you bread, forget about the size of the bread. They say they brought you bread, okay? Divide the bread into 2 equal half. So it's not the, you are not going to weigh this because either the bread is big or small. Is it 2 of you, maybe twins, 2 children, they share it equally. So all you need to do is know that half belong to this person, half belong to this person. Don't ask me the size of the bread, but the bread, irrespective of the size, should be shared equally between the 2 people. So it's the same thing. So if the normal distribution or any of these distribution is bilaterally symmetrical, like a bell shape, one side is the mirror image of the other. So if you can divide into the middle, one side will be half, the other side will be half. So if you put half plus half, you go to 1. So that is why the intelligent people can say, okay, let's assume that the area under the graph is 1. 1 means 100%. That is 100%. So all you need to know, okay, if you divide into half of it, the proportion will be 1/2, 0, that's 50%. The other one will be 50%. So that's how the idea of the area under the graph. So the area under the graph, because you already know that even the probability cannot be greater than 1. That is a certainty. All the whole probability cannot be greater than 1. So the whole area is the whole probability 1. So now, when you begin to conceptualize the area, if you look at the middle 95, you know how normal distribution came. Intelligence will discover that many variables go as the value like height. Actually, no, let's use weight, like a variable like weight now. In the population, most biological variable like weight and many and social science variable, they follow normal distribution. How do they follow it? How did people discover? They discover that as the height, like a weight, increases, in the people in that category increases also. Like now, to find adult that's 35 is very rare, 35 kg. But the adult that is 40 kg will be more in number than the 35. The one that is 45 will be more in number that is. So let's say the scale, horizontal scale is the value as it's increasing, as it's increasing, as it's increasing toward the right. The number, that's why the height of the graph is going, the vertical is the frequency number in that category. So as the thing is increasing, the value is increasing along here, the number in that category increases until it reaches a point. Like for example, height for weight of adult now, 70 maybe here. Once it's going beyond 70, the number in the population that have the value more than 70 will be reducing than the one that is 70. So as increasing, so the people that weigh 90, they decreasing less than people that weigh 80. People that weigh 100 are not in number, they are fewer than the people that weigh 90. 120 are fewer than people that weigh 100. That is the logic. So there are many variables that follow the same pattern. So they follow normal distribution, because as the number, the value of that variable increases, the number of people with attribute increases until it reaches a point. If it increases further, the number of people in that category decreases. So if anything follow that, so it was found that, okay, in between, if the reference point is the middle, then the mean is the one. That one that is in the middle has the value that the most people have, the highest frequency. That's why it's peak. And it happens that if you divide all the value, you add all the value and divide it by the total number of observations, it gives you the which is average. It will be same damn value that is in the middle that most people have. That's why it was discovered that for anything that follows normal distribution, the mean, the mode, and the median. If you arrange in ascending order, that value will be in the middle. 70, let's say 70 will be in the middle. Then 70 will be the value that most people have. Then 70 will be the mean. So mean, mode, and median the same for anything that follows normal distribution. So understanding probability distribution, especially the consonant probability distribution, once you understand normal distribution and how people now say, okay, just use that graph to depict the total area is 1. So it is now believed that to the extreme tail of the distribution are the people that have extremely small value. To the extreme tail, to the other side, the people have extremely high value. And in the population, the people that have extremely low and extremely high are few. That is why people now consider 95, the middle 95. What is the value that 95% of people in the middle have? So the remaining 5% will be the extreme. So the remaining 5% will now be people that have extremely low, which is 2.5%, and people that have extremely high value, which is 2.5%. Both of them make up the 5%. So it is believed that is the logic behind normal range. When you calculate, you take blood sugar from thousands of people, you now calculate mean standard deviation. So any value, the people usually approximate 1.96 to 2. Doesn't matter. 1.9. So any value that is less than 2 standard deviation and value that is more than 2 standard deviation, we believe that is not normal. That's why they give you normal range. The normal range they give you is what they get from the mean plus or minus 2 standard deviation. They calculate the standard deviation, they now multiply by 2. So anybody that is less than minus 2, they remove that 2 standard deviation from the mean. The value you get will be the boundary for the extremely low value. To add the standard deviation to the mean, 2 standard deviation to the mean, the value you get will be the boundary for extremely high value. That is how that was the normal range was actually discovered. So let's come back to this. You can now see now how T relate to the distribution. So one thing, the T distribution was actually invented or discovered for extremely small value, but as the sample size is a really small sample, as the sample size increases, you discover that the T also look like normal distribution. I think that's all this graph on this slide are showing. Now, I don't know if there's any before we move. Then the critical value, okay, I think I've just said it now. You know, if you, what I just explained here, once look at the T distribution degree of freedom of 12, for you to know the critical value now, the critical value is what the standard deviation that correspond with the middle 95%. For degree of freedom T12, the critical value will be 2.2. If the sample size increases, the critical value will be less, it will be close to 1.96. As the sample size increases, the critical value will begin to. That is why if you look at the table of T, can you see? You see the critical value is bigger when the degree of freedom is very small. Let's look at 95%. 95% confidence level, you're talking about 0.05. Look at this column. You will see that for 1 degree of freedom, the critical value is 12. And for 2, 4. For 3 degree of 3, can you see? As the degree of freedom increases, as the sample size increases, the critical value becomes lower and lower and lower, because you know that T, the base is wider. So it makes the critical value to be big. But as this approaching normal distribution, when the sample size increases and the freedom increases, the degree to shrink, the base begins to shrink close to normal distribution. So the critical value will be approaching that 1.96. Look at it now. At infinity, can you see? Down for 95% confidence level. At infinity, that is when the sample size is extremely large. So the degree of freedom is infinity. The critical value is 1.96, exactly for normal distribution. So I don't know if before we move, we want to see Z. We have just explained the Z distribution and normal distribution. So in trying to find out, to test the difference between two groups, why using t-test or z-test? The choice of, you will discover something even in many statistical package, you will not see anybody. Why is it that z? It's t, not z. So we want to look at t-test versus t-test. So before we move further, if there's any question. You know that this is a workshop, and some people just came in. Dr. Afolabi, because I sent something to the platform, it's for those people that have enrolled. So
actually came in later.
Yes. So
I don't really know where it is started. I just saw on the WhatsApp page that
I put it there that is for the people that have enrolled for it. So maybe
okay.
Maybe you do enroll.
I'm actually lost.
You are lost. How?
Yeah, I don't know. You know, I didn't know when they started. I don't know how.
No. We just start by first. We are starting today. This is just the workshop is for 3 days. First day is for t-test, which is what we just started. So tomorrow will be the non-parametric counterpart of t-test, and the next tomorrow will be for sample size determination using WinPepi. How to calculate with software. It's practical. That will be on Sunday. But today is for t-test. Tomorrow will be for non-parametric counterpart. This will be McKinsey. So the workshop, we are going to run the analysis. So that's why I'll be putting it on the platform. I don't know, people don't read it. So those of you that are just banking, so you make your subscription. Unless you want to continue. Good evening. Okay, someone is greeting. So, any question on this before what we have done?
Good evening, sir.
Good evening.
Good evening, sir.
Good evening. I'm listening.
How are you, sir?
You have a question?
So, please, sir, my question is, I noticed that you mentioned t-test, you mentioned z-test. So, because I know that, okay, you said t-test is used when the sample size is less than 30. So, are you saying that when it is more 30, the equivalent is z-test?
That is what we are. I wanted to ask question on the one we have discussed, because we are reaching the, and that's the next slide. We want to discuss z-test versus t-test.
Okay.
But before that, I just say I entertain question on what I have discussed on the shape of the t-test and the critical.
Okay.
That's why.
Okay. I think that's the distribution you were discussing. So what it means is that when the sample size is higher, I noticed that the graph, and like I totally understand what now mentioned that the base will be lower. It means that a higher proportion will now be closer to the middle. That you will have, because it's larger. Is that why the curve seems to shrink?
Yes, now the curve is the base. It's just like something you have elastic. The volume is the same. You can change it. You are just changing the volume is the same, because the area under the graph is 1. For both is the same. For both T and the Z and T. But the Z is taller. If it's taller, the base will be smaller. If it's just like if you have 2 ropes, you fold them as in the like a shape of bell. So if one is taller, of course, the base will be narrower. I don't know if you understand now. If you have two rope now, you are trying to use to explain like this. If you have two rope, if you try to make the thing to be taller, the base will be smaller. If you want to make it flatter, the base will be this, because it's the same length. So it's the same thing with the T and the Z. The T is taller, the base, and the T is just one shape. Yes, I mean now. The area is one, and the standard deviation is one. Everything about it is one. Standard deviation is one. Variance is one. You know, variance is a square of standard deviation, and standard deviation is square root of variance. If you square one, it's one. If you find square root of one, it's one. So everything about it is one. The area is one. The standard deviation is one, and the variance is one. That is standard normal distribution. So the other one now, they just want to mimic normal distribution. So it's the same bell shape, but it's flatter. The smaller the degree of freedom, the flatter it is. I'm sure the 1 degree of freedom is just flat like a line. As it's becoming 2,
Yes.
fold up. You need to fold up. You need to fold up. You know. So as it reaches, when the sample size becomes extremely large, that is the degree of freedom become extremely large. It now be like normal distribution. So can you see? That is how T distribution relate to normal distribution. And the chi-square also relate to normal distribution in different perspective. I think we discussed it when we were talking about chi-square distribution. F distribution also relate to normal distribution. As the degree of freedom increases for all of them, they approximate normal distribution.
Yes.
All the continuous probability distribution, behave like that.
Oh, wow, it now makes sense. That statement, that's what it means.
Yes. Now, Z versus T. You will see why you hardly see anybody using T set test or comparing me. The reason you go to see. Now, what this one is like algorithm. How do you know which one you should use? Generally, Z tests are used when we have large sample size. That is when sample size is greater than 30. That is when the degree of freedom is around 30 or more. Because the sample size now we're talking of the degree of freedom is n-1. I think we are not going to be talking of that one here now, because that is rudimentary. So one thing I want to advise everybody, either you are just coming for the first time or you are attending, I want everybody that want to be listening to me to go and subscribe to the video. Do you know the reason? A lot of women, some questions people will be asking. When we talk about basic concept, they are all there. So Dr. Aduse can testify to that, because recently she has watched all those videos, all those things. I'm just, whatever you are seeing here about even continual probability distribution, they are all there. We iron them out. It's sometimes that when people now ask questions, we begin to go over it, but for you, if you really want to grasp it, you subscribe, and it's win-win situation, because it doesn't cost you anything to subscribe. It costs you nothing. It costs you just small amounts, less than what you use to share your phone to subscribe and have access to those materials. Generally, Z tests are used when we have large sample size. T tests are most helpful with a smaller sample size, less than 30. That was the reason the person that invented it or discovered it, that was why he did that. That's Gosset. Both methods assume a normal distribution of the data, but the Z-tests are most useful when the standard deviation is known. Z has to do with population. So you cannot use Z-tests if you don't know the population standard deviation. So you must be able to know the population, that is the previous work. You must have an idea of the population standard deviation for you to use the Z-test. Now, with that, Z-test, population greater than 30, then you must know population standard deviation. Now, let's compare the two. Do you know population standard deviation? Standard deviation, not just standard. Yes. If it is yes. If it is no, go for t-test. If you don't know population standard, you cannot use z-test. So you go for t-test. Now, if you know population standard deviation, if the sample size greater than 30, if the sample size is less, the z-test is not appropriate. So if the sample size is less, is not greater than 30, you use t-test. Can you see? Because t-test was designed for a situation where the sample size is very small. So can you see now? So when the sample size is very small, you go for z-test. And when you don't know this population standard deviation, you go for t-test. When the sample size is very small and you don't know the population standard deviation, you go for t-test. So for you to use the z-test, you must know this population standard deviation, and you must have a sample size that is large, not less than 30. Now, logic. Out of 3, if you look at what do I call it? 3 options here. 2 are favorable to t. Look at this red something where you take decision. Out of 3 options here, 2 are favorable to t-test. Only 1 to z-test. Even to me, when the sample size is large also, we have already demonstrated that even the t-test approximate z-test. T distribution is like Z distribution. So you will not see that whether the population, whether the sample size is very small or large, t-test is appropriate. I don't know if you get the logic. I don't know if there's any question concerning what I just said now. Whether the population, whether the sample size is big or large, T is appropriate because the t-test, yeah, is favor. You cannot use z-test when the population, when the sample size is very small. So you go for T. Even when the sample size is very large, in that case, the degree of freedom for the T has increased. And it's like Z, it's like Z distribution. So that is where you will have even used Z also. T is appropriate. Does it make sense?
Please, I don't. I'm trying to figure it out because I'm sorry. This particular one, I'm still confused about it. I've seen where we've used t-test for substances that were more than 30, 40, 100.
Yes.
So my question now is that do that t-test that we see when we run SPS, is it Z? Is it Z telling us?
Is T. That's what I'm telling you. Okay, look at the previous slide. We already said that as the sample size increases, the degree of freedom increases. Look at this blue something. Look at this graph in the middle. T distribution with 20 degree of freedom. 20 degree of freedom means sample size 21.
Yes, sir.
Because the degree of freedom is n-1. So 20 degree of freedom means sample size 21. Do you get it now? Look at T distribution here. T distribution n close to 30. You see, the sample size is close to 30. It has not even reached 30. But once it even reach 30, it's like normal distribution. It's like normal distribution. So when the sample size increases, even the T.
So once it reaches that 30 or more than 30, it's already close to or normal distribution.
Exactly, normal, exactly. So you can still use T because the T is like a Z. And the Z, for you to use, you must have population standard deviation. But T, you don't need to have population standard deviation. And when the sample size increases, also
it's already approached the population.
Like their distribution. So look at it. We look at it. Okay, let's look at the degree of freedom 30. Degree of freedom 30 here. Can you say 1.697? Whereas for sorry.
Yes, sir.
It's 2 point. Look at if you are looking 25%, 95% confidence level. Look at under degree of freedom on T 30 is 2.041. It's close to 1.96. Can you see? Once it goes further, look at when it is 100, it's 1.98. Can you see? It's close to that because it's reducing. Okay. It's close to that 1.96, which is the critical value, standard normal deviation for 95% confidence level. So when you are talking of 100, when you are talking of, like, can you say 100 now, 1.965, 1,000, 1.96. When you are talking of higher value now, it's close to Z. Does it make sense?
I don't understand.
That is why, even in any situation, that's why T you are using, whether the sample size is large or so T.
Oh, I now understand it now.
That is why T has come to replace Z distribution in many instances. Does it make sense? Now,
yes, sir.
Formula for T, you know that I said something. T test is comparing two mean, whether you like it or not. It can be one sample, even if it is one sample T test, you are comparing the mean for your sample with a mean in the population, right? So it's still the only thing that in the population you don't have access to the sample, but you have access to the summary, what they have summarized before. I say this is the mean in the population. Your home, your data, you have access to the mean and the data set. So you are still comparing two mean. If it is two group, of course you have access to the two data set and the mean. And if it is, when we are talking of two means now, it can be pair or non-pair. So what you have here now, look at for you to conceptualize, in fact, not only T, for you to conceptualize statistical tests, the simplest way to understand is two T tests, independent T tests, two groups like this. That is the simplest way to understand all statistical tests. As I've said before, statistical tests, they are the same thing. They're just different, it's the same thing, cloth in different name. What you look at, you are trying to compare observed value or observed difference and expected difference. As when you see the word hypothesize value, mean expected value. Another name for hypothesize is expected. And what it means that the expected value when non-hypothesis is true. That's why the word expected or hypothesize is the same. What is there is expected value when non-hypothesis is true. Non-hypothesis is true when you say there's no difference between the two groups. Imagine now you measure the weight of adult, public and private, maybe students or teachers in public and private school, measure their weight, average weight. Or urban, rural. You have access to the mean value for both of them. Now, non-hypothesis will say that there is no difference in the weight, mean weight of the teacher in the public and the private. There's no difference. Of course, if actually in the recent, there's no difference. If you remove one from the other, it will give you 0. If you say there's no difference in the value of this, if you not say value A minus value B, both of them, there is no difference in their value. If you remove it, it should give you 0. So now, because in your study, in research, you are looking for difference between groups. Like for example now, this issue of the weight, public and private, or blood sugar, public and private, or urban rural, or hemoglobin concentration, but let's say blood sugar, public, urban and rural. Blood sugar, urban and rural. We are looking at the difference. If actually there's no difference, if this one average is 60, the average of this one should be 60. When you remove 60 from it, it give you 0. Listen. So, but in no hypothesis, there's no difference. That is, what is telling you is that if there's no difference, if this one is 17, this one should be 70. When you remove it, it should be 0. They should have the same value. Of course, your hypothesis is stated in 2 ways. No hypothesis and alternative hypothesis. And in the no hypothesis you are testing. I explained that in our video on introduction to inferential statistics. Why you test no hypothesis. Go and watch it. Why you test no hypothesis. Why you don't test, it is no hypothesis you test, not the alternative hypothesis you test. When you watch, you see that. Now, if there's no difference, the no hypothesis will be true. Because no hypothesis, there's no difference. But if there's a difference, at the end of the day, no hypothesis will be false, will not be true. So what you get is observed value, what you observe, okay, and you do your study, you get that urban was 65, rural was 60 in the blood sugar. You have seen the difference of 5. So that particular difference is called observed difference, or you can call it observed value. Look at this with the x1 minus s2. This is urban, this is rural. You remove the difference is s bar x minus bar x1 minus bar s2. That is the observed value, what you observe. And the difference you see is the observed difference. The hypothesized difference is in the population is telling you that the mean one, that is the mean for the urban minus mean rural is this. That is hypothesized value. So what you are testing is per se, you want to remove the difference between the observed difference and hypothesized difference. If you now, you call it observed value minus hypothesized value or expected value. If you now find a difference from what you observe and what you expect, that difference, normally you say, oh, since there's a difference between what I observe and what I expect, that should have this difference I'm seeing in this blood sugar amount is a real difference, because I can see that urban is more than rural. I can see. That is, if you try to remove, if there's no difference in what you observe and what you expect. What you observe is your observed difference. What you expect is expected different. If both of them are the same, and that expected difference is the difference you expect if no hypothesis is true, if there's no difference between them. So you see the logic now. Now it doesn't stand like that. If you now remove the expected from the observed, you get a value. That value you cannot say is a real difference until you divide it by the standard error. And that standard error is the measure of inherent variability of the attribute in the population. If you go and watch the video on Introduction to Inferential Statistics, when we talk about sampling distribution, we talk about standard error. You will notice that there are 2 things standard error will tell you. The standard error will tell you if that particular attribute vary a lot in the population or it doesn't vary much. Then it may tell you if your estimate is close to the population parameter or far from it. How does it do that? When the standard error is very small, it may be telling you that, oh, your estimate is not too far from the population. What you estimate is not too far. You estimate your sample is not too far from the real thing in the population. But that's not what we are using, we are concerned about now. What we are concerned is the second aspect of it. If it is very small, it shows you that that attribute does not vary much in the population. If you calculate standard error for height and weight, you discover the standard error for weight will be more than height, because weight vary more in the population than height. So if standard error is very small, it may mean that the attribute is very close. The variability of the attribute is not much. So, and that is what forms the denominator for your statistical test. So because if you say, okay, yes, you have done the blood sugar, the urban more than the rural, can't you see the mean blood sugar for the urban? Can't you see is 60 and that of the rural is 65? Or sorry, is something. The one for the urban is 65 and the rural is 60. Can't you see that urban is more than the rural? But you can be sure that even among the urban, that the blood sugar is 65, higher than the rural averagely. There are some of them that have far lower blood sugar than even the average from the rural, even than some people in the rural. Even the rural, you say their blood sugar is smaller than the urban. There are some of them that have far higher blood sugar than the average for the urban, even for more than some people in the urban. So even among them, there are variations. So what we have, the difference you just see when you calculate average for both of them, it doesn't make any sense until you compare it with how vary is it? What is the variability of that thing in the population normally? If the variability is even bigger than the difference you are seeing, that shows that you cannot say that this difference is significant. So that is why the intelligent people, in trying to calculate statistics, they now put that the difference you observe as the numerator and the inherent variability, which is the standard error, as the denominator. So when you now divide, you know, if you put something, if the numerator is bigger, far to offset the denominator, the value will be greater than 1. If the numerator and denominator are the same, it will give you 1. But if the numerator is far bigger than the denominator, it will be greater than 1 when you divide it. But if the numerator is far smaller than the denominator, it will be less than 1, give you 0 point something. So if for you to say this difference is significant, we expect the numerator, which is the difference you have observed, to be far bigger than the denominator, to the extent that it will be greater than 1. Not only greater than 1, it will even reach a critical level. And that's, oh no, this is the critical point that this difference we have observed is not due to chance. It's not just, it does not just come by chance. It's a real difference. That is the logic behind all statistical tests. All statistical tests. That's just the simple logic behind it. You may see some variation in the way they now calculate, but is that the logic behind all the statistical tests? You look at the difference, the difference between what you observe and what you expect at the numerator, and the denominator will not be the standard or the inherent variability. So if that thing very much inherently, normally said, any little difference you see will not be, any little difference you see cannot be significant. It is when the inherent variability compared with that difference is very small. So the difference is like the inherent variability is small. That is not, oh, these different. So don't let this one confuse you. For you to get it, I think let me use this formula for sample size for one sample t-test. In what we are saying now is that if it is one sample t-test now, it is easier, not only even for pair sample t-test also, one sample or pair sample, it is the same logic for you to understand what I'm saying. Look at this X bar is the mean you have just calculated. This mu 0 is the mean, the one they gave you in the population. This is standard deviation, in standard error rather. You know, standard error is standard deviation over square root of sample size. Standard deviation S over square root of sample size. That is standard error. So you can see the different denominator and numerator and the inherent variability as measured by the standard error denominator. And standard error is standard deviation over square root of sample size. So when you divide it, if it is big, it's not telling you that, oh, it is greater than 1 and reach a critical point. It's telling you that this difference we observe is not by chance because it offsets the inherent variability. For it to be bigger than 1, that shows that it's bigger than the inherent variability. That's why it will be far greater than 1. That's just the logic. So this one I'm showing here, don't let it confuse you. This is just a formula because it involves two groups. This one is a standard error for the two groups. It will be complex. But you don't need to cram it because it's just for you to get the logic and know how to use computer to run it. So I just went to use that one to explain because it's simpler. Square root of standard deviation over square root of sample size. That's the standard error. Then when you are calculating for two groups, so if you look at it like, if you combine it, standard deviation over square root of sample size for group 1 plus standard deviation over square root of sample for group 2. What they just do is that if you remember the square root of sample size, so if you extend the square root to everything, normally this one was not under square root. If you not put under square, you have to square it. That's the logic behind squaring this one. Normally is standard deviation over square root of sample size. It's the sample size n that has the square root. But if you now want to solve it, for you to accumulate the two at the same time, you want to extend the square root to above. All these s, they don't have square root. The square root was not under them before. For you to not put them under square root to get the same answer, you square them, which is also 0. So that is the logic behind this one. So you don't need to bother. Now, what I just want you to observe here is that we have already said that if the hypothesized value, if the null hypothesis is true, this n mu1 and mu2 should be the same. So it will be 0. The difference between them will be 0. That's why it's out of the equation here. So it just x1 bar minus x2 bar over this standard. That is formula for t. So just leave that one. Now, for you, the t-test you are talking of is a form of parametric test. Parametric test. That is, it's a test you carry out with the assumption that the variable you are dealing with follow a theoretical distribution. And that theoretical distribution is normal distribution. We have already said it before. The first theoretical distribution now is the basis for hypothesis testing, normal distribution. If you look at the relationship between T and Z distribution, you now know that for you actually to be able to use t-test to compare difference between two groups, that variable must follow that normal distribution, must be normally distributed. No, that's not but that's number one, the most important assumption. The number two assumption, these assumptions are rated according to their importance. Number one is the most important. Number two is the second most important. 3 is the third most important. The number 4 is the least important. It can be evaluated if nothing will happen. Number 3 and 4 are usually evaluated, especially number 4. but they are least important. They are the least important. Number one, normal distribution. Number two, homogeneity of variance. Homogeneity of variance means you go to see when we run it, you see, it just means that even though the two groups you are comparing, the mean, you are comparing the mean, you want to see that the mean are different, but their variances must not be different. That is, how widespread around their mean must not be different. That is, even though the mean for this group is 60, the mean for this other group is 65, you can see the difference. But they should be, how close the observation are to the mean should not be different. That is, to certain extent, to the same extent, they should be close to their mean in each of these two groups. So one must not be too widespread than the other. So for the two groups, you are comparing the value average distance from their mean of all, it's the mean they present to you, but is the mean of all the observation. So individual observation, how far are they from the mean is the measure of variability. This is the which you use your variance or standard deviation to measure. So it must not, that is, it must be the same. It must not be too different from the two groups you are comparing. That's the meaning of homogeneity of variance. If you are doing an overnight, you are comparing three groups, mean of three groups. It's still there also. If the mean are not different, you can't be comparing them. But they are, for you to use term parametric test, there must be homogeneity of variance. Each of the group, the spread should not differ. In each of the group should be the same. Even though it appear to as if you are observing different, they should not be too different. When you put it to test, it should not show that the spread different. That is homogeneity of variance. Data must be measured at least interval level. Interval level. You that are listening to, okay, I don't know if it's a workshop, so that I don't do. So let's talk. What does that mean? That thing, data must be level, but the measure on at least interval level. Actually, as people don't usually think of it. What does it mean when they say interval scale? So who will tell us what does it mean when you say the data must be on at least on interval level? Who will tell us?
It must be continuous.
Yes, it must be continuous. Continuous. No, I know it's well, must it be? Is it continuous? No, not necessarily continuous. But when you say interval scale, well,
That's a true zero.
is it continuous? Well, that's it. Okay, interval scale does not have 2 0 original. They say at least on interval scale. If you remember, Dr. Aduse, if you remember, if you have watched the under the descriptive statistics, yes,
it's arranged in groups, sort of.
So if you remember
Interval.
under interval scale, scale of measurement. Interval scale means that it's number. That is, the distance between two. You're like
in
when
proportions equal.
Yes.
Is it proportion equal now? Equal interval.
No, it is the interval between each group. That's the way the groups
You must
are.
be able to each different value. Yes, you must
be able to measure the difference.
Quantify the interval. Yes, equal interval. You're like
quantify.
Yes. So he's talking of quantitative variable. That's all. He's just talking of, because interval and ratio. When you say at least, after interval is ratio. So he's telling you it must be something you measure on interval or ratio scale. When you say at least on interval, you mean either interval or ratio. So it's talking of quantitative variable in that sense. Well, somebody is talking. Now,
yeah, okay. I had a question.
Yeah.
Concerning that homogeneity of variance you spoke about. Okay, no, I have two questions. The first one was that formula you showed us. You showed us a formula that had x1 minus x2 in bracket minus mu1 minus mu2. Now I know that the x minus x1 is the population, then the mu is the parameter. Sorry, is the sample. I mean population sample. Now, for that one, I'm guessing it's for comparative studies. Since we're looking out for difference. So I can just confirm if I'm saying hello.
Yeah, go on.
Ahead, yes, this one. So yes. So oftentimes we're measuring. We say, oh, we want to see the difference. So was that what you were trying to depict here? That is the because I know that if you're trying to say, okay, there's no difference, for example, shouldn't that be that that is the difference between wait, I don't even get it confused. When you say there's no difference, doesn't mean that the difference in the population, there shouldn't be any difference between the population and the difference in your own sample. That is,
Okay,
if you're looking at, let's say, if the population urban rural, doesn't that mean that? Oh, okay, you're not hearing me.
I'm hearing you.
Hello?
We are hearing you.
No, sir.
I'm hearing you.
Okay. So I'll say that if we are doing rural urban now, and with this your formula, what it means is that if we're looking at formula hypothesis, what you're saying is that using that there's no difference between rural urban for population
For that,
and
you want to measure
rural urban for sample. So I'm now wondering why you now, after you calculated, you ended up with x1 minus x2. That's my first question. Now, the second one, I noticed you were talking about the homogeneity of variance, where you talked about how, yes, even if the means are different in ANOVA or in t-test, but their variability should be equal, should not be vary around their mean. So this variability you're talking about, is it like standard deviation?
Yes, now
Is that what you mean? Because I know standard variance is SD squared. Okay.
Yes, standard deviation of variance. Those are measure of variability. So standard deviation and variance, they are the same, just like water and ice block.
What does it mean? So why does it? So what is wrong with it when one of them, let's say in the case of ANOVA, when one of the means variance is more? What does it mean? Like, I want to just have an understanding.
Yeah, it's just like well, they are not comparable. It's just like if you are conducting tests for people, you now say
yes,
you are trying to say who is the best in certain thing, and somebody receive,
yes,
you want to know the best among two people. You now favor another person. Maybe somebody has been in the rural setting, maybe student that have been in a rural school. Okay, maybe you are trying to intelligence IQ, who has higher IQ. You now bring people. Somebody is from rural, somebody from urban. At the end of the day, if you look at it, if you put the same IQ test for them, you are going to, there is a problem, because in the sense that maybe you brought your IQ test from urban center, that thing that the urban person is already familiar with, and the person is not familiar with. At the end of the day, you are trying to compare, but you now see that because of the differences in their location, they are not comparable. In comparing two means, you say you are comparing two means, it means you are comparing, right? Somehow,
yes.
If the variability is not the same, it will offset it. This lady has, where is Yetunde? He has similar problem with her work, right? We compare two groups. When you do the scoring, there's one that has more variability. The mean is higher in one group than the other group, but the other group that has lower mean has more variability. When we now want to have a cutoff point, okay, cutoff, anybody that have above this value will be the good. The one that have lower mean have more people scoring higher than that value. Can you see? And it has lower mean. Because it has more standard deviation, the standard deviation is bigger. when we say standard deviation, in the sense that the mean is small, but you have extreme values. Some people are maybe score less, some score high. So when you are now having some cutoff now, because you have some people that have extreme values, so you now give impression that the score, you know, when you are doing cutoff, usually use a particular value, maybe that value is above the mean. But the person that has scored lower averagely, because it has some value, they have some, that group has some extreme value up. You can't give impression that more of the people score high. I don't know if you understand me now.
Okay, pulls it. It pulls your mean.
It's not actually, it didn't put the mean is still where it may, number one.
No, because what it means is that if there's an extreme value for it, so let's say you're having most people having, like, let's say 2 number, then you have one that has a very high value, one of your extreme, that it will give a false impression that the mean is high.
No. Even apart from pulling the mean, it's not even a matter of pulling the mean. What we are saying now is that it's not even a matter of skewness, though you can call skewness, but what we are saying, the one that has higher variability, we have extremely small value and extremely big value also. I don't know if you understand me now. It's just like in school, when you want to put the best student, they have 8-9 subjects. Both of them score averagely 70%. When they do average of all the 9 subjects, both of them score 70%. Who is still the best? For you to know the best, somebody, that's where most of the time that ladies usually beat men in the class, because if really a man score the same thing as a woman averagely, you can be sure that that woman will be better than the man. The reason is that most of the time, if the man that score this, you discover that he may score extremely high. You can score 90, 100% in some subject, and the other subject score 30 something and score low. Somebody that scored 100 in physics, in 90 something chemistry, biology, 80 something, and when it comes to maybe language, when it comes to another thing like language, history, he scored 30, so it doesn't like. But somebody that is more consistent scores 75, 72, 60 something, you know, in all those subjects. It's not too far from the mean, even though the mean is 70, the value are not too far from the, so the standard deviation will be small. But the person that score, even the mean is, even somebody can even score higher, like the boy can even score average 75 more than that. He may face some subjects, maybe he score 40 or 39 in history. You see, he doesn't, or CRK, he doesn't like it. They score 100 in physics, score 100 in mathematics. At the end of the day, they can give the best to the person that even averagely score lower than, because the person didn't fail any of the course. I don't know if you understand me now. So, so extreme, that was what happened to Odusholu's data. The non-support group, they have higher variability. They said that they are extremely low value and extremely high value. Whereas the supported group have, you know, the variability is smaller, and at the end of the average is still higher in the supported group. But when you are having a cutoff now, it gives the impression that there are many people that score high mark, high score in the non-supported group, but there are also many that score very low. You will see some situation where in a particular group, that's where you see people that did best and did worse. Whereas in another group, you see, you won't see the best, you won't see the worst there. It's more consistent. So that is why we are comparing mean, but the variability must be the same, because it will somehow affect the your comparison. So for you to use a parametric test, so the homogeneity of variance must be
equal.
Yes,
I now understand. So this, can you explain this slide now?
Yeah, which one?
This one that is up now. You know, I was explaining to you how when you look at difference, because I'm now wondering why it ended up being x1 minus x bar 1 minus bar 2. If you're looking, if you're saying that the difference in the population.
Okay, wait. I was explaining. You were not following. This x1 bar minus bar s2 is for your sample. That is, this is what you observe. When you are doing a study, we have observed value, we have expected value. Observed value is when you do your descriptive statistics. What you see are your observed value. Yes, I'm not. But what you expect, if that particular thing you are looking for, there's no difference in the population, what do you expect? That is expected value, which is hypothesized value. So, mu1 and mu2 telling you that if actually there's no difference in these two values in the real life, this is what we were expecting. But this is what you observe. Can you see now? It's the difference between, that is why even when you get to the issue of expected value, observe value, that's what you'll be seeing, even in chi-square. In any statistical something, observe value, expected value. So observe value is what you get in your research with your sample. Expected value is what we expect it to be if actually there's no difference in the two groups. So what that means,
I know.
whatever the value, forget about whatever the value of mu1 and mu2, whatever the value may be. If actually no hypothesis is true, there's no difference between mu1 and mu2. Because mu1 minus mu2 are the observed difference. If there's no difference in the two groups, if there's no difference in the two groups, they will be the same. If one is 17, the other will be 17. So if you remove them, it will be 0. You know, it's the same logic when we use when you come to odd ratio. If there's no difference, we divide, because it's about division. Ratio is about division. So if you divide the other from there, it will give you 1. That is why we use 1 as a reference. We are talking of confidence interval crossing 1. But here, we use 0 as the reference. Confidence interval crosses 0, because if there's no difference between the two groups, when you remove the one from the other, it will be 0. So if there's no difference, the expected difference will be 0. That's why mu1 and mu2 will be 0. If it is 0, that's why it's out of the equation. Does it make sense? Does it make sense now?
Yes, it does. Thank you so much, sir. Yes,
that is why you will not
see
it. You will not see it again in the equation, because it will be 0.
Okay.
Yes, that's why it now
Okay.
But the logic flow like that from up down. That is how the logic flow. It is the expected difference will be 0 if no hypothesis will be is true. So that is why this one is out. Any other one? Okay, I think we have explained homogeneity of variance. Hold on. This boy is just calling. Hello?
Sorry,
you want to give her, okay. You want to give the cloth, okay. Hold on, you will come. Also, eh? Okay, sorry. Now, then independent. The last thing, independent. Independent means that the two groups you are measuring, the two samples you are comparing, the measurement must be from different people. But if you look at it, I've already said that this is the least important of the criteria, assumption or criteria. It is the most violated, because when it comes to pair sample, dependent sample, that one is violated before and after. Because the measurement you take before and after, they are from the same group of people. You take before from the after. So that one is violated. That in pair t-test now, this number 4 is violated. Now, I said something. Sometimes there are some tests you see carry out. If all these things are not met, t-test and ANOVA, they are robust tests. A robust test is a test that is still valid when not all the requirements for using parametric tests are met. And that is why this number 4 can be violated in pair t-test. Even sometimes also, number 3 can be violated. Especially if we are dealing with when your sample size is very large. For example, if you do like Dr. Oducholu's work, it's like SK use 1 to 5. 1 to 5, 1, 2, 3, 4 is arbitrary value. Strongly agree, strongly disagree, neutral, agree, strongly agree. It's you that give 1 to 5. Who told you that strongly disagree is 1? You know, it's like a scale. Just like if you measure the disease severity, severe, non moderately severe, mildly, all different, moderately differentiated, undifferentiated, all these way we use to categorize cancer. You can just give arbitrary value. Those are because those variables are ordinal, they are not interval. We just give the arbitrary value. But sometimes we do, if the sample size is very large, you can use parametric, especially if you have calculated the average. For example, now in Dr. Odusolu's work, when you have applied the Likert scale, you now discover that you can, when you are calculating this your WHO 2, in trying to calculate the composite something, you calculate the average. Once you have calculated the average, you have introduced decimal into it. So it's not because the original 1, 2, 3, 4, 5 has no decimal. But at the time you group about 5 questions together or about 10 questions, you calculate the average for them. It has introduced, because you cannot always have the average whole number. Once it has introduced that continuity, you can use parametric test. So you can violate it and use parametric test there. So that is why this number 3 and 4 are usually violated. But the other 2 are the most important. The first 2 are the most important. But when you run the analysis, when you see that median and mean, they are far apart, or you see that the variance is bigger on one side than the other, standard deviation is bigger on one side than the other, you know that no. The best way is to use a non-parametric test. So when you observe that, you have to, like this your friend's work now, ZMINA. So most of the tests there are not parametric, but there's some few, because it's dealing with 3 groups. Sometimes you see, it's not because you see the mean value for the 3 group different. Of course, that's what you are testing. But when you now see the standard deviation, it's a similarly small, similarly big in one than the other. You know that you cannot, it will not be right to use ANOVA. You now use Kuka-Wallis. I hope you understand the meaning of Kuka-Wallis.
Yes, sir. Sure. Please, sir. I'd like when you were explaining that Likert scale thing. I went off. Like I was following that thread, but my this thing went off. I was you were trying to explain why, you know, on that ordinal. So you know, when you group it, then you take average of something that ideally you're not supposed to take average. Then what now happens? I was trying to get it.
I didn't say ideally you're not supposed to
What
take.
you were saying.
It's a workshop. Don't worry. Let me share. Dr. Shevnes, can I share some of your work, the Word document to see? Can I share it? Dr. Odusolu? It's not there. Just, Dr.
I'm here.
Can I share?
I'm here, sir.
Let me share your work. Let me just share the Word document.
Sir, we are learning.
They will see what I'm saying, because it's good for you to have the understanding. Not just the cramming. Let me just quickly open it. Okay. Where is the Word document I open? So you can you see? Can everybody see what I'm sharing? If somebody can see, let me know.
Yes, sir. Yes, sir. We can see.
I want to show you part. Look at the question are just all those strongly agree or whatever. Like a scale. So if you look at it now, this is on a scale of 1 to 5. Here, comparing two groups. If you look at it, the average 3.5 plus or minus 1.1. You cannot compare. I will use my witness. I cannot use t-test because the score are 1, 2, 3, 4, 5. I cannot use t-test because they are ordinal scale. Those 1, 2, 3, they don't even exist per se. It's we that gave. They are not the real value of all those things. It's we that human being that gave it. But somehow, when you now, can you see now? The domain, there are 6 questions or 5 questions that make up this domain. Those 4 questions that make up physical domain, there's a way to calculate it. You calculate the average, divide by this, multiply by. But in the process of calculating average, multiply by 100, it has introduced decimal. In that case, it becomes a continuous variable. You can use student t-test. Can you see? So here now, when I was comparing individual, I used my witness. But here, the domain use student t-test. It's parametric. But there's another one here. Look at the same and look at this one. This is raw score. This raw score is a way they call it a non-transform score. You know there's a way they say you -4, multiply by 4. All those gimmick they just did, but eventually the score, look at the average, is around 13 something for each physical domain. Because it's not the raw something. So student T. This one also is for passive scale. This scale is also 1 to 5. But the way each of them is 1 to 5, just like the other one. But there's a way
What is that other range mean? That range beside it, what does it mean?
range.
Beside the table 30, the range after the mean plus or minus, there's the range 5 to 20.
And that is the
Is
smallest
that
to minimum to maximum now. Minimum to maximum, that's the range. You know the example of the word you, I don't know, maybe it's from Zimbabwe. You send. That's why what they put there. That's why is the minimum to maximum. That's the range. The minimum to maximum. So now look at this one. Passive social support scale. The question that gave this one, they are
Okay, so is this the way? Is that the way to? Is this okay?
Are you listening? Am I? What did you say? What did you say?
Is that the way to present? Yes, sir.
Yes, you can present like that.
Now, I'm trying to ask if
what?
Okay.
So this one, this significant order is about 4. Is it about 4 of them or 3 of them? We calculate here the average.
Oh.
So, you know, we didn't have the 4. We count the 4 and now calculate. So by calculating average, it has introduced decimal in. So that's why we can use student T. It's not the original. It's not as if maybe this significant order is not originally measured. It's not that 1 to 5. There are 4 questions that were measured on a scale of 1 to 5. We now added the question and now divided by 4, calculate the average. So because of that, it's a derived this thing. That's why you can use student T. So you can see there are some situations you can, even when something was not in all the interval scale, you can still use it, you can still violate it based on some situation. That's what just I wanted to demonstrate so that you see. Let's continue.
Thank you, sir.
Okay. Yeah. Now, the type of t-test now, one sample T, independent sample T, and paired sample T. Now, let's quickly look at each of them. One sample T, you know, t-test is about comparison of 2 mean, whether you like it or not. In one sample T, you have only one sample, but they give you a value in the population you are comparing. comparing your value with. Say, oh, similar study have been done before. The average blood sugar was this. So the only thing there is that you only have the average blood sugar from the literature there for that one, but you have access to only one sample, which is the sample you have. Of course, you can calculate you have your average also. You calculate the average, you have the average for your sample and the data set. So that's what we call one sample t-test. So if you look at this by X is your own average for your sample, mu 0. You know, mu is donation and is used to denote mean in the population. By X, mean in the sample. So go on, under descriptive statistic we discuss is all there. Under descriptive, the video on descriptive, we show that the Greek letter is for population, Roman alphabet is for sample. So that is comparing parameter and statistic. This X bar is statistic. This mu is parameter. It's in the population. So X minus mu over standard error of this of the mean. So when you, which is standard deviation over square root of sample size. That's all. Now, mean sample target value of the population means sample standard deviation number of sample tests. This is description of the formula. Now, this is an example. Now, I want to the first example for student T for this one sample T. The following is the age distribution of 20 victims of a disease during an outbreak in a country. The age was recorded in years. That's for 20. These are the ages. If the mean age of the victims in a neighboring country was 33 years, can we say that the mean age of affected victims is the same in the two countries? Can you see? This data you see is the victim of Ebola in the country. This is the age. It was when I was doing the training, one of the epidemiologists, the team in the country then came to attend the training and I brought the data. Said that I don't see Ebola victim. I don't know, as if they wrote their name there. So that's why I just say victim of a disease. What difference if you say Ebola? You will write the name of those people there. So the 33 years is just arbitrary. I just put that one there. Then all these other one ages are real age of people that had Ebola in the country then. Now, if you are to compute it using the formula, from the formula now you can see that you must calculate the mean, you must calculate standard deviation. If you are to use hand to calculate, you must, from this formula, T, you want to calculate S bar minus MU. MU, you have given us 33 in that question. You must calculate the mean for the own data set, standard deviation, then name for you to calculate T. Now, look at the X listed here. If you sum every sigma X, it's 791, the total age. So mean is sigma S over N, and there are 20. So the mean is 39.55. You see, sigma mean addition. So by X, sigma X over is 791 over 20, the mean. So for you to calculate the variance or standard deviation, you know the formula, this is the formula for variance. So if you want to do that, X minus S bar. No, for you to reach standard deviation, you must calculate variance. So X minus S bar, this is the mean, deviation from the mean. You remove this 33.55 from each value it gives you. If you try to add all this together, it will give you 0. Because as much that are negative are also positive when you add it together, because the mean is in the middle. Some value are less, some value are more. You know, you remove mean from the value. So for those values that are less, when you remove mean, to give you negative. Those values that are more than the mean, you remove mean, to give you positive. So because the mean is in the middle, as much that are below are also above. So if you try to add them together, 0. That was why intelligent people say, okay, let's square it. When you square x minus s bar, this is x minus s bar is deviation on the mean. This is square deviation. When you square it, you remove the negative. So when this is square deviation. When you add everything together, this is what called sum of square. So for some of you that attended the ANOVA training, you remember sum of square. This is the origin of the sum of square. When you sum of square, you square, you just form a square deviation of the mean. But in short, sum of square. So this is sum of square. So when now we want to calculate the average sum of square. The average sum of square is the variance. X sigma x minus s bar square over n minus 1. So the average is calculated not divided by n, by the degree of freedom. The degree of freedom here, what we mean is that if we have calculated the average now, you can multiply the average by 20, it will give you the total. The total is already fixed. So in that sense, you have the mean. The mean is already involved in this calculation. You cannot, because the value, this sum of square, now, you cannot, all of them can vary except the last, except one. All of them cannot vary because the total is fixed here, because the mean, we have the mean and the number. The total here, who is writing on the chain? So, what's that? So, now let me point. The total. So the total is fixed. All of them, each of them can vary except one of them, maybe the last or whatever, can vary there because the total is fixed here. So the degree of freedom is n minus 1. So when you divide by degree, it gives you the variance. Variance is square mean deviation from the mean. Square, this is deviation from the mean. This square deviation from the mean. The mean of it means square division. The mean of it is calculated by dividing by n minus 1. The mean, when you now divide by 20 minus 1, divide by 19, give you this. This is the variance. Then the standard deviation, because you are square here, you want to go back to the original unit. You calculate the square root of the variance, it gives you this. This is standard deviation, 12.3734. So look at the formula for the T. The mean minus the mu, the mean from the population, over standard deviation over square root of 20. Sample size, when you do it, it gives you 2.367. So the T is 2.367. So if you go and look at the statistical table now, to really know if this T is significant, what is the degree of freedom? What is the degree of freedom? It's 19. Let's go to that. It's 19 and 20 minus 1. So let's check the degree of freedom. This is the table. The degree of freedom of 19, what is the critical value? Under 0.05, 95% confidence level. Is 0.023, right? Is 0.023. You cannot see?
No, but it's tiny. It's really tiny.
Yes, sorry. I can see 0.023. Okay, don't, let me do something.
So where is the 0.023?
Wait, I want to do something. Maybe you'll be able to see. Can you see now? Can you see it? Can you see the degree of freedom of 19?
It's better now.
The degree of freedom of 19.
It's better now.
Look at this.
Yes, sir. It's better.
0.0.
So
This is
what
Yeah,
can
yeah.
we
Under
see,
this column.
sir?
This is the
Yes.
column. The third column. 0.0.
Wait, so it says 0.
0293.
Okay.
0.09.
Why is 0.
Sorry,
Is it
2.093.
not, is it not 2.0? I'm seeing
Yeah,
here.
it is
2.093.
2.093. Sorry, it's 2.093.
Wow.
Yeah. So 2.093, and your value you got is more than that. Is more than the critical value. The value you got. Let me zoom back. The value we got is 0. Look at it now. 2.3. So
2.3.
it's greater than the critical value. So you can be sure that the p-value is less than 0.05. Yeah. So now, if you want to run it,
0.5. Okay.
yes,
Okay.
you want to run it. So who has the data set? Victim. I think the data set is Ebola victim. Who has the data set there? Nobody. Okay, let me go and look for it. Oh, I think I open. Yes, let me open it. Open the data set. Hunger, Ebola victims, yeah. You can see the data set. Can everybody see?
Yes, sir.
Yes.
Yes, sir.
So you now say, analyze. This is the age of the 20. Can you say 1 to 20? This is the age. You analyze. Compare means. Go to compare means.
Sir, you will share twice.
No, you can see the data now.
Yes.
You can see the data, but you're already clicking on analyze.
And yeah, you should be seeing. If you are seeing the data, you should be seeing that one now. Analyze.
But that's the thing, I'm not seeing it.
Wait, maybe it's not that one you are seeing. Then don't worry. If that's the case, don't worry. Let me share again. Maybe it's another thing you are seeing. Can you see it now? Can you see the data set? Can you see analyze now?
Yes, sir. Yes, sir. Yes, sir. I can see it now.
There are.
Oh, that means it wasn't the data set.
So it was another one you are seeing. I opened through another one. Okay. This is 20. Can you see 20 of them? These are the age. So analyze. Compare means.
Okay.
One sample test. Age. We are comparing age. I now come. You look at it because test variable age, then test value. You know, it's one sample test. There's a value they have given you in the population, which is 33 years. You will not tap. You see 0 there. You now replace it with the test value. Now say okay. I don't know if you can see the. Let me share. You may not see the output.
Share your output.
I've shared now. Can you see? I've shared the output. Can you see?
Yes.
This is the output. You can see.
No, sir. Okay. Yes.
This is the mean. The mean we calculated 39.55. This is the standard deviation we calculated. Yes. And the T, you calculated 2.367, and the degree of freedom is 19, and the p-value is 0.029. The mean difference, the difference between the other one and the 33, you know, the one they gave us 33 and this one 39.55. The difference is 6.55. So the confidence interval of the difference. So if the difference, can you see now? Does it cross zero? The confidence interval range from where to where?
It ranges from 0.76 to 12.34. So it doesn't cross zero.
Yeah.
It crossed zero now.
Sorry, it's above. It
because
says it is above.
Okay, don't worry.
This is
Don't
12.
fight.
This is 12. 12 is to your right, so it crossed zero. Zero is in your number
I
line.
thought it's more than zero. Like it doesn't cross it.
No worry.
Because if it's 0.76,
This is 0.
0.76
your
is higher
0.76 is
than
before
zero.
Minus 2, don't worry.
It doesn't cross.
Don't
It
fight.
doesn't cross zero.
This is
So that's
1,
significant.
2,
Okay, it's not
3,
significant.
4. Now, it's from 0.76, right? It's 0.76.
So that's between 0 and 1.
It's not between 0 and 1. Yeah, it's between 0 and 1 to 12 point something, even above, just going from here to something. So you say it's cross zero. How did it cross zero now?
Okay, it didn't cross zero.
So if it has crossed zero,
if it's minus something.
It will be minus. Thank you. To start with minus, it will have a value minus, cross zero to positive side. So that's how you know if it cross zero. It will start with minus and then at positive. So it's significant. If it's not going to be significant, it will start from its minus and cross to the other side. That should have cross zero. Because knowing that when the null hypothesis is true, there's no difference. The difference will be zero if you remove the mean of one from the other. If let's say the mean, the mean you are testing and the one in the population is the same. When you remove it, it will give you zero. So what this confidence, what this one is telling us is that the difference we have seen in this work is 6.55. That is your work, your sample. That's how it's different from the one they gave you in the population. But in the population, you are 95% confident that this difference I see from 5.5 here will be between something like 0.76 to 12.34. It can be any value in between the two. It can be 0.68, can be 0.78, can be a 1, can be 1 point something up to 12.34. So you can assume any value. You are 95% sure, confident that any of the value in between the two values is suffix. So you don't actually need the p-value to interpret, but you know, in our environment, you have to just put it there because many people don't understand how to interpret p-value. So interpret confidence interval. And in what we have done, we have just done two methods of inferential statistics here. We have done hypothesis testing, which is the t-test. It's the t-test that gives us 0.029 as our p-value. That is hypothesis testing. Confidence interval is different completely. It's different. It's a different method. So it's another method of inferential. But when you do your table, you put t-test and confidence interval. It's more like a repetition. You are showing two inferential methods. But actually, if you want to go, you should go for confidence interval because it gives more information than the p-value. The p-value tells you if it's significant or not. That's the only information it gives you. The confidence interval gives you that information also and other two information, giving that this confidence interval is giving you threefold information. Why hypothesis test, the p-value give you only 1. The p-value tells you if it's less than or equal to 0.05, it's significant or not. But the confidence interval, by looking at it, if it doesn't cross 0 or not, we know if it's significant or not. But it's able to tell us the difference and also give us, that's another information it gives us. Then the third information is also give us a range of value within which you are 95% confident that you find the population value. Because what you are just getting, you just give us, is what you get in your sample. And your sample, in as much as you didn't study the whole population, your statistics can never be equal to the parameter. You need to study the whole population for your statistics to be equal to parameter. If you study the whole population, yes, whatever you get is a parameter. In as much as you took sample, so what you get is statistic is still far from the parameter. So that is why the confidence interval now give you a range of value within which you can be confident that the population value will be in between. Is there any question concerning that? Any question?
No.
Simple. No question, right? We proceed. Is it that is, maybe I should be calling him to ask question. Dr. Aduse. Because if you don't ask questions, it's either you are confused or you know everything. You know, if you don't ask questions, it's either that you are confused or everything is clear. Is it clear or is confusing?
This is very clear.
Very clear.
Very
so look
clear,
at these are the results we just generated now. That's what I just put on the slide here. Very simple. So let's go to the next one. We have just, it's 3 types of t-test we want to look at. We have just looked at one, which is one sample t-test. Let's look at independent t-test now. Independent sample t-test. Otherwise known as independent measure t-test or independent sample t-test or simply student t-test. Because that was what the person that first described t-test, Go said. It's actually independent sample t-test. He explained. It was later that more people also started bringing other things. Now, there are 2 experimental. What are the conditions that warrant this? Even the first one we did, the one sample t-test is only applicable in a descriptive study because there is no experimental design that doesn't have comparison. There's no experimental design you do, you say you are comparing with the population. No. That one sample test is only applicable in a descriptive study. But independent sample t-test now can surface in comparative study, which is analytical study like the one most of you are doing, like the one Ugo you did, the one yesterday you did. They are comparative study. They are analytical study. That's a cross-sectional analytical study. Now, it can be experimental study also. Like the one this Dr. Emina did now. If let's say it's 2 groups now, it will just be independent sample test. If let's say there are 2 groups. So, experimental design, there is one experimental group and one control group, or comparing means of 2 groups in observational study. So, in this situation, it can even be case control, observational study, case control, study, cohort study, experimental design. So, no form of study, any form of study, but there are 2 independent groups. That is what, and what you are measuring, your outcome measure is quantitative. Example, table below show that the number of days lost to absenteeism per month over 15 months rather, due to sickness in the mining and the construction industry can can we say that the mean number of days lost differ in the two industries? This one, look at it, just show you data set for two. You know, when we try to demonstrate all this, we usually use a method that may be too very funny. Begin to imagine. This one parametric or whatever. But the issue is that we usually choose example that is simple to calculate with hand so that you can see the logic. Though it's the same thing. It is either the sample size is large or not. Of course, if the sample size is large. But when we're using hand to do it, you are wasting time. To be wasting your time. So we usually use example that you can easily conceptualize, use hand to calculate, and now run, and now see the way. Either you use the hand or you use machine, you get the same answer. So these are number of days lost. You can see the number of days. There's no and a half there. It means say 3.5, whatever. Number of days, more like this whole number. Doesn't matter. And the sample size for each of them is 15, 15. You see. Now, remember t-test for sample size even less than 30, so that one is not a big deal. We have already shown the formula before. So I try to compute it just like before. You know, this is the formula. For you to, in the formula now, you have to have mean for group 1, mean for group 2, standard deviation for group 1 and 2. Look at it. So the mean for group 1, the summation, all the summation for group 1, 87, divided by 15, it gives us the mean, which is 5.8. For group 2, the summation of 56 divided by 15 gives you 3.73. This is the mean. So move further to calculate the variance. Remember, standard deviation. This is L minus S bar 1, S1 minus S bar 1. Then square of it, sigma, that is summation, sum of square, divided by the degree of freedom, which is 15 minus 1, 14. Give you the variance for group 1. This is variance for group 2. That's it. Standard deviation. Group 1 is square root of variance. Give you 2.04 here, 2.085 here. You feed in the mean for the two group and the standard deviation and the yes. And the end. So you get your answer is 2.742. If you go and look for the degree of freedom is what? What is the degree of freedom? The degree of freedom is 28. N minus 1 plus N minus 1. N1 minus 1 plus N2 minus 1. Or you say N1 plus N2 minus 2. So you know that 50, 15. 50 for 15, 30 minus 2, 28. Or 14 plus 14. So the degree of freedom is 28. So if you look at the critical value, the value 2.74 is still greater than for the degree of freedom 20. Let's check. The degree of freedom.
It is greater.
28.
Yes. Look at the degree of freedom 28 under this. Look at it.
2.048.
2.048.
Is it 2048?
So what we calculated is still greater than the critical value. So I say that, sorry, it's significant. So what you get is 2.74. So let's run it. So who are the sets that that they lost to absenteeism? That's the name of the data set. Who has it there? Okay. Let me share. Let me go and look for the day loss to sickness. Yeah. Look at it. I don't know if you have seen it. Let me share again. So have you seen it? Can you see day loss?
No, I'm showing you.
There are two groups.
Okay.
Can you see? If you look at it, it's enter in series because there are two groups, right? Separate independent group. Group 1 from 1 to 15. Group 2 from 16 to 30. So when you're having two separate group or separate group, that's how you enter in series. So if you look at your this in Dr. Iguilo, your work, is when the other one hand you add the other one. Is that not the way you enter it? Hmm? Dr. Odusolu? Hello?
Sir.
Your own.
Yes, sir.
So
Yes, sir.
that it's two group you did. So like Dr. Odusolu's own is from 1 to 305, then 306 to 610, 610, right? That is because there are
Okay.
two independent groups.
Okay.
Enter in series.
Yes.
In series after the
There are
other.
two groups. Yeah. So it's parallel.
No, it's not parallel. Series.
Oh, it's series.
Series, not parallel.
Series
Sorry.
after the other.
When you finish one, you
Yes, it's
continue.
series.
So like this one, I look at it.
Paired, that is.
1 to 15. Then from group 2, we now measure the second one, the mining construction from 16 to 30. If there are three groups now independent, then from 31 to 45 will be for the next one. That is, whenever you have separate group, it must be entered in series. And you now have a variable which is group that will differentiate them. Can you see now? For all the first one you wrote 1, 1, 1, 1, 1. But that's the same thing we did in your data. Like Dr. Uzoluna, the first group, even though you just enter, you went to analyze parallel, you enter it or you even try. You enter your friend that you send, that one that says you want to analyze herself. You want to put them in separate Excel. I just laugh at her. If some people share, I don't even know. So if let's say you didn't no intervention on time, you will not do this exam. You will not do this exam. So doesn't even know what she's doing.
I need to laugh a bit.
What is it? You are laughing? So
I said I need to laugh a bit.
I know that you yourself you have demonstrated your ignorance also, but your ignorance is better than our own. So at least be able to enter from at least in the Excel sheet, I enter from 1 to 305 and from 306 to 610 at least. But the only thing you didn't do, which I now did, is for you now create a separate group in the front after the serial number, and now order your the first group, and now put 1 in all of them. Yes, and I now code it 1. Then the other one, the other 305, I code them 2. That's the way to do it. So that group variable is the one that separates them. So they will enter them series. Okay, let's run it. Yeah, in series. I'm just explaining this because when you are creating your questionnaire file or when you are entering your data, you do that. So even if you put in separate Excel, but for you have to put it together like that. Now, before you can run it.
Okay, before we run.
Okay, sir.
Before we run.
Okay, sir.
The groups, group 1, group 2, what did they represent?
The one group is mining.
Group
It represent the mining something. You know, if you look at the question, let's go back to that question. The question, what we are running, let's go back to it. Why is this? Okay. where is the? I'm trying to. Okay, I'm trying to see the PowerPoint I open. I don't know why it's not coming out. Okay. Look at it now. The mining group, the construction group. So, listen now. So, since they are separate group, if you look at the way we enter the mining from number 1 to, because there are 50-50 of each of them. We enter the mining from 1 to 15. Construction from 16 to 30 in series. Yes. So, but if you don't do it like that, it's not enough. It will be confusing unless you show a variable that separated them. So the variable that separated them now is this group. I don't know if you understand me now.
Which group? The variable that separated is which of them?
Is the group. Look at it. We now put the group here. So look at they lost now. They enter 1 to 15. Number 1 to 15 for this. From here now is down to 30 for the construction. But if you put it them in series like that, but you must be able to separate them. So I will now create a variable here, group. For that group 1, I will call it group 1 for all of them, then group 2.
It's very clear.
That's the way to do it. So you now say analyze. You know what Dr. Dusolu did was to go and copy, even though he has already entered it in series. Now copy this one and put in front. And so she now confused herself until, simple thing, just to know that you just need to create a group that will separate the two. That's okay. Okay. Analyze, compare means. Independent sample T test. The one we did before was one sample T. This independent sample T. Now click on it. They lost the variable we are testing. Now, group variable, can you see now? That group variable is separated, you must bring it here. Merely you bring it, it will give you question mark, define group. Here, that's why it's good. We have coded group 1 as 1, the other one as 2. Just put it how you code it. In some situation, if you use, maybe you type mining, you have to type it there. You have to, if you didn't code it, like, look at it. Let me go back. Let me cancel it. So, wait. Let me show you the label. Can you see? No, I coded is labeling, It's 1, 2, I wrote there, but I label it. It's the labeling. We put it, I show that one. What we enter there is 1 and 2. We now label it. But if we didn't enter, we just label, we just type mining and construction there. When you are now doing your T-test, it now has you. It now asks you. You have to type mining. What to enter there, you have to type mining and construction. If you don't. So that's why it makes it easier when you code everything, you enter as numeric. You just put a number there so you know what to put there. So what I put is 1 and 2.
So if you type mining, it will look good, it will not go.
It will not go because it's not mining and enter. But if let's say it's mining and construction, we type there, we enter there. That's what you have to type there. You get it now?
So even though they said use specified values, so the values can be string.
Yes, now that is the value that was specified in your data. Let me see, let me see, because there's never in. Let's see.
And maybe we should try to.
Let me see. He's not taking it. Can you see now? Can you see? He's not taking because It's numeric. That particular something I've entered is numeric. But if let's say it was not numeric, it was string, it will take that something. But if it will take what to enter there. But if it is ANOVA, in fact, by the time you enter ANOVA, any variable that is not numeric, you will not even see it here inside display. That's why in ANOVA, in fact, you have to code everything, anything you want to use. If it's ANOVA now, any variable that you didn't even enter, you didn't put as numeric, you will not even see it. So that's why it's good to code it. So you now click OK. So let me share. Can you see? Can you see the results?
Yes, sir. Yes, sir.
You see the mining 1515, that's the sample size. You see mean 5.8, that's what we calculated for mining. 3.73, that's what we calculated for construction. These are their standard deviation you calculated. Can you see? You can calculate their standard error by dividing by square root of sample size. The standard deviation divided by square root of 15, it will give you this standard error. You will see the first thing we do here is level test for equality of variance. It's testing for homogeneity of variance to see if the variants are the same. Now, this, if you remember, the 11th test is F test. If you remember when we did ANOVA, we talked about F distribution. We said that F distribution is not only for ANOVA. You can use it to compare two variances. If you remember, look at it. F is the same F distribution you use in ANOVA. So the F can be used for ANOVA, can be used for comparing variance, two variances. So he compared the two. If let's say the two variants, if you look at it, you know that it's the same. Look at the standard deviation 2.0 something. This one 2.0 something. Look at their standard error 0.5, 0.5. You see that it's the same. There's no difference. So the test, look at it. If let's say they're different, it will be less than the p-value here will be less than 0.05. But it's very big. So the probability that they are different is the difference you see, whatever little difference you see to chart is very high. So there is no difference in the variances between the two groups. Yeah, what do you say?
I said there's no difference in the absenteeism from duty, the same across mining and
as per no difference in their variances, in their measure of spread.
This level test is now that test used to decide whether it is parametric or non-parametric.
Yeah, that's used to test for homogeneity, yes, for homogeneity of variance.
So in addition to that normal distribution, you also use this test.
No, yes. It's different condition. The normal distribution is one condition. This one, homogeneity of variance, is another condition.
So can you select? Is it good for you to select, or is it good to have to do both of them? When you're trying to test for normality.
If you look at if you calculate the median now, you're going to see that it's the median and the mean, they are very close.
Yes, so that is tell you.
Or you go and do the exploration. If you do exploration, you use this Kolmogorov spin-off test and Shapiro-Wilk test.
That's the one I was going to ask you. So that's the one that that's the one that is used to test for normality.
Yes, you use that one to test if the thing is normally distributed.
Okay.
Yeah, so.
Then I used to hear something that if standard deviation is 2 times, should not be. There's one rule
Is
we
what?
always have.
Is what?
There's one rule I used to hear, whether 2 times away from the mean or something. I don't know if that's true, or 3 or something. I've heard such a thing.
People just come with funny things. To make it this thing, it's better even when you plot. What do I call it? What do you call it? That's the graph. when you plot histogram or stem and leaf, you can look at the shape, yes, but looking at shape of histogram or stem and leaf is very subjective. So it's still good to quantify. And the best way to quantify is to do those tests. It will quantify if it's significant or not, if it's different, if it's significantly skewed or not. So this is 11 tests, and there's no difference in there.
And it says that 11 tests is for numerical. The tests that do T, that do maybe F.
What are we saying? What are you saying? Okay, this thing you are doing, you are comparing me. Is it not for numerical variable? If you are talking of proportion, will you be talking of theta? You'll be talking of chi-square now. So,
talking of variance, true. Okay.
So, homogeneity of variance test, you can see that you notice that the mean differ. But what we are testing here, of course, if you even know the mean is the same, you won't be saying you are comparing the mean. We want to show that for you to use parametric test, the variance should not differ. Can you see now? So the variance is not different now. We now come to the T. Look at the T, we calculated 2.742, and the degree of freedom is 28. And there's provision. If you look at there are two lines. Equal variance assumed for first line, equal variance not assumed. In case the 11 test is significant, showing that there's no homogeneity of variance. Okay, you can choose the one down. You assume that there's no equal variance, and choose the one down. Well, so look at the p-value, look at the T, look at the degree of freedom 28, p-value 0.011. So look at the mean difference. If you remove this from this now, it will give you this mean difference. You remove 3.73 from this, give you mean difference. So look at what of the confidence interval? Does it cross 0?
No, sir.
No.
Does not cross 0, yes. So now I want to rerun the same thing for you. You will see the result. It gives out the same thing. They want to change something there. Go to analyze, compare means, dependency. So what I want to change now is that under this group, this group variable, I want to change group 1, I want to change to 2. And I change this group 2 to 1. So what I did before was to say the first group 1, I put 1 because that's mining. I coded 1. And I put 2 for the second one. What it does is to remove 2 from 1 to give us that difference. But now I want to put construction first. And I put mining so that I remove mining from construction. You know the mean of mining is higher than that of construction. You see what will happen. Can you see? Yeah, you see now. Can you see the result?
No, sir. You didn't share the second time.
It's there now because let me reshare. Now, so you can see now. So you will see, you will see that it just put negative, negative. What's the difference between the one we did before, this one and this? It just put T, it just put negative. Mean different, negative.
To the other.
I see the lower and upper confidence level, negative to negative. Can you see? It's the same thing.
Yes, sir.
What you just do, look at it, say the difference minus 2.067. Everything is still the same. Even the T is the same value. Just what you're telling is that the first one, we remove smaller mean from bigger mean. This second one, we remove bigger mean from smaller mean. It will not give you negative value. It's the same. You will see in the former one, the confidence interval. Look at the confidence interval of the difference. It's from 0.5 to 3.6. But the second one is from minus 3.6 to 0.5. Can you see? To minus 0.5. It's still the same thing. So the confidence interval, even for this one, so it does not cross 0 from minus to minus. Does it make sense?
Yes.
From minus to minus. What is just telling you from minus to minus, and the mean difference is minus. It's just telling you that when you run your analysis, you want to remove bigger one from the smaller one. So if you want to change it back to doesn't give you, all you need to do is to go and, when you are running it, that group, you swap it. When you swap it, it gives you what you're looking for. Because sometimes you may look at, if I run it like this one now, I get minus. What I will do is that I will not say the answer is minus T. I will still put T. I will put the difference to be 2 points. I will remove minus. But the confidence interval, I will not say, I will now swap it. No, this one is from minus 3.6 to 0.5. I will not say 0 plus 0.5 to plus 3.6. The lower will be 0.5 and the upper will be 3.6. Does it make sense? So that's where you can confuse yourself under the confidence interval. Does it make sense?
Yes, I does. Yes.
So there's no question for that. Dr.
Question.
Adusi has left. Dr. Adusi has left. Let's see her again. Okay. The last one.
There's a question.
What do you say?
I have a question.
Okay, go on. Answer.
If you choose equal variance not assumed,
yes,
is it not a non-parametric test you are doing?
No, it's not a non-parametric. You see t-test, they just adjust tests. It's not non-parametric because they just give you, they just tell you, well, I don't usually use it, but they just tell you that there will be change if there's equal variance. If you can only decide to choose that one, if the 11 tests show you that there's no equal variance assumed. So when you now choose equal variance not assumed now.
What I mean is, under that setting, are you not supposed to use the non-parametric method?
That's what I'm saying. If I discover that there is no equal variance, you opt out to go and use non-parametric method. But that one does not stop you from getting information about the confidence interval, because the confidence interval is different from the T. It's only that they just run it together. The T is hypothesis testing. Confidence interval is a different thing. So in that case, you can adjust your confidence interval. Like for this person, I just analyzed our project now. That Dr. Emina. Say you are hearing, you look people. Dr. Iguilo.
Yes, sir. Yes, I'm here, sir.
That Dr. Emina. Yes. When I was comparing you wanted to do different, you know, the funny things they just want in their result. Different. Even though they don't know the meaning.
Yes, that is
different. So now because she did pre and post, and there are 3 groups, pre and post. So the difference between pre and post for the 3 groups, I've done it.
Yes.
When you see the standard deviation of the difference is, you know, you can see that there's no homogeneity of variance, because even the standard deviation, the issue of mean and median, you can see that there is much difference between mean and median, and you can see that there's no homogeneity of variance among them. So I use Kukawalis to compare the 3 different.
Okay.
Now that is instead of using ANOVA, but because for me to do the different in different, I have to use, you know what I use? I use post-op and just use LSD. No, it's the LSD that will help me get the different. That is, it will remove each from each other. You know, she has
yes, you want to do that permutation for you.
Eh?
It's to do that because it's 3 groups.
Exactly. Thank you. Permutation. Yeah, thank you. To do the arrangement because there are 3 groups. You will remove you hold Tejo show.
This one from this one.
Which you
this one from this one.
Exactly. So that is how you can get your different. So you just use, even though I use non-parametric, but I have to go and use under and over and do post-op to get that thing out to do the different. When she presented on Tuesday, you go to see the different. So yeah. So
But she has to be able to defend it. Because it's always like,
but
it's advanced.
you have to understand what you do.
Exactly.
All these different post talking.
Okay, no problem.
Post talk, I get that one. I'm saying she herself has to.
No, the work was good. It's good. Though. The work looked fine, Sha. The work looked fine, and
okay.
So
okay, then
that means able to pass. She will pass the book. She will pass the book. The work is okay. Yes. Unless you doesn't pass the order.
What that means is that this, experimental groups is very difficult for you to get similar groups. Because people always say, "Oh,
don't mind them. She has said she cook a lot of data there. I discover.
So hard.
And at the end of the day, now see effect of it. Don't mind them.
So hard.
They cook a lot of data. And if somebody tell lie, you need another lie to support the lie to continue. So, okay, this is the output of this one, Justin. Lastly, let's just do the last one. Pair sample T, otherwise known as matched pair t-test or dependent t-test. It is used when there are two experimental. Yes, McNema. No, McNema is for categorical now. Is when your outcome is categorical, but this one is pair t-test. Outcome is quantitative. So this is otherwise known as matched pair t-test or dependent t-test. So just like the independent also, you can use it in both experimental design or non-experimental. But most of the time, this is commoner with experimental design because it is very rare to do observational study before and after like that. It can happen, but it's rare. So you can be sure that most of the time is experimental design for this. And it is found that the experimental design pair is of higher quality than the independent. And that's the mistake how many people will do. So when you want to know the effect of all those your experimental, you don't need to have any control. They are saying, if you want to take measurement before and after, if you are going to do this and you take measurement before, you administer your this and take measurement again, you don't need the control. You don't know. So like the work this lady did now, it's like 3 work he's doing. Because for each step you show the control, you do take baseline and do what you want to do. And now take after. Each of them, you can analyze it. If there's not going to be any difference, the statistics will bring it for you. So people they don't know that. So there are 2 experimental conditions and the same participant took part in both. Those are the scenario we use petty test, or comparing means of measure taken before and after an intervention or experiment, or comparing means of repeated measure taken from the same group in observational study, or comparing means of peer observation measurement from the right and left eye. There are some things that occur in pair. Yeah, that's the one that is common when it comes to observational study. Like eye, intraocular pressure, right eye, left ear, right ear, left ear, right arm, left arm, right leg, left leg, right breast, left breast. Think of anything that occur in pair in the body. You can use pair T to compare any measurement. So let's look at the example. The table below shows anxiety score before and after counseling of 9 persons prior to disclosing to them their HIV status. Did the counseling significantly influence their anxiety score. So before you before you disclose HIV status to people, if you don't cancel them, no, by the time you declare, you do it, they may misbehave. In fact, they may do something funny that they can even commit suicide. So this person should try to look at the anxiety level before counseling and after counseling. Of course, you expect the anxiety to reduce after counseling. So if you are looking at this value now, you can see that most of the value after counseling are lower. There was the logic. You remember, here, I keep on emphasizing this. The difference between the pair and independent is that for independent T, you are looking at the difference between two means. If you remember the independent sample T, there is bar X1 and bar S2. You are looking at the difference between the two. So independent T look at difference between two means. But this one, even though you take measurement before and after, you are not calculating their mean and the before and after and removing. No. What you do is to remove the value before and after. Look at the table. This cancelling before, after cancelling. The difference, you now remove this, you subtract after from before. In substitution, it may be before from after, it doesn't really matter. But there's a difference, you remove. This is the D. Is the now calculate this, the mean of the difference. Can you see? The mean here is the mean of the difference. Even though there's a mean for this group, but that's not what you use. That's what the statistic use. It is there. But what you are using is the difference, the mean of the difference by D. So you now calculate the standard deviation of the difference. How to calculate that? The deviation of the difference, the square deviation, and now calculate the variance. Can you see? Look at the variance. Look at the mean of the difference now. 300 is the difference, addition of the difference, divided by the 9. It gives us this. The variance of the difference. Can you see? When you calculate the variance normally, the way we do it, and you get it, and standard deviation of the difference. So pair T is the difference. Can you see? Mean of the difference over standard error, which is standard deviation of the different values of sample size. Simple. It gives you 4.3. And the degree of freedom is the number is 8. So you can see that this thing for the degree of freedom of 8, if you go and check, let's go and check for the degree of freedom, because the degree of freedom here, because there are 9 of them. So 9 minus 1 is 8. Let's check the table. Degree of freedom of 8. Let me zoom it. So look at it under this third, the middle row. Can you see the degree of freedom of 8 is 2. The critical value is 2.306, and what we calculated is 4 point something. So you know that it's greater than the critical value. So it will be statistically significant. So
that makes so much sense.
Yeah.
When you were talking about sample size, about how it is the mean. If you remember,
that what?
The mean of the difference. You know when you're talking about it's the mean of the difference.
Yeah.
It is different.
I
now remember that sample test you were teaching.
The mean of the difference and the difference between me. So here is the mean of the difference.
For the pairs. Exactly, that for the pair is the mean. I now understand what you
mean. The mean of the difference for the pair, yes. Even for if you are looking for sample size for it, it's the same thing. The mean of the difference in the first one. Not different between me. Okay.
Yes, sir.
So let's run it. Let's run it. Anxiety before and after. I mean, anxiety before and
Okay,
after.
so while you're opening,
Okay, go on.
okay,
Go on. I
while
want
you're opening,
to open.
okay, I
Go on.
just wanted to confirm when they say the difference of the difference, it means that because you're having, for example, if you're having two groups, for example, you're having one, let's say one experimental, one control, and you're doing before and after. So what it means is that when that's difference, first of all, between your experimental and control, there's a difference you get.
Yes, yes.
Now, this one is the before, and this one is for the before. Then there's now an after where you still have an experimental and a control. So that difference is now the difference in the difference in that difference. So that difference between the group in the, so it's, how do I even, is the difference in the difference between the experimental and the control before and after. I don't know if I'm explaining it well. Is that what it means?
There are two differences, Madam.
Exactly.
There's a difference between the control and the experimental group. That's before now. Then there's another difference between the control and experimental group of the after. Are you getting me?
That's what I'm just trying to confirm.
So your differences will be at two stages. One before the your before. You understand? Your before within the group. How do I put it now? Before you started,
understand it.
Okay. So you have two differences.
Okay, please, let her continue. Okay, Dr. Jane, you can continue, please. Sorry.
Okay, so your difference between your control and your experimental group before your intervention, and then you now have another difference between your control and experimental group after your intervention.
Yes.
Then you have again another difference between
those two differences.
Your before, exactly, the two differences that you got from your before and another the difference you got from your after. Differences between them.
Yes, thank you very much. I just wanted to confirm that's because that's what I know of difference in difference. I want to make sure there's not something.
What is the difference? What do you know about it?
No, that's what, okay, Professor Shibogo says it like that. He calls it different in different. That's the way Jane explains, the way I know it.
Okay, what is it? Yeah, let me explain again.
That's the difference. Okay, let Jane
explain.
Okay.
I was saying, let me say what you said. That you said that you know what I'm going to do. You said that before within your control and your intervention, there is a difference at baseline. Then after your intervention, you want
which is your end line,
experimental group and the control. You measure the difference again.
Yes.
Then you now the difference, initial difference and the later difference. You now measure the difference again. Difference of difference. Abi, that be so.
Yes.
Confuse everybody. Okay. I want to hear what Jane said that they say different. Yeah, Jane, say it again.
Oh, okay. So now the difference between the control group and the experimental group at your baseline, then you have again your difference between control and experimental group at your end line. Do you understand? Then you now subtract the difference between the baseline and the end line to get another difference. So difference in between, your before and then difference between your after.
Okay, you see, that is, you just mix it up. Yeah. The difference is, for experimental group, the difference between before and after, baseline and after, there's a difference. Then for control group, there is a difference between baseline and
experimental group, again, there's a difference.
Yeah, the experimental group, there's a difference between before and after for experimental. And for control, there's a difference between before and after. The difference of those different, that's the difference. Can you see now? Is where you took it.
Because you're looking at the experimental.
Yes, I mean now. So you are not starting with the difference between control and experimental baseline. No. What you are doing is that before and after, you look for the difference for experimental. Before and after, you look for the difference in control. Now try to see if experimental have more. You understand me? If the different, there's a different in the two different. That's a different in different. And that's what I did.
Okay, this is where I always mix it. Okay,
Yes.
this is where I miss it all the time.
Okay.
So you have to first
This is good. Thank you to go.
Yeah. You know, before and after each of them first, before you now, that before and after the change now, the difference in the change. You know what change now before and after for experimental and control. Then the difference, is there any difference in the change? If there, you should expect that there will be more change in experimental than control, because control also there will be change.
Control.
There will be more change. So the
the control. The difference between the control and control now is trying to help us to know that the changes we are seeing is not by chance. It's not by chance.
Because sometimes even without doing anything, there are some things that change. So you want to remove that effect. You want to know there are some things that change even without doing anything. People improve naturally now. Even education, so people get aware of something even without your health education. People improve over time. So there are some changes that may have occurred without your intervention. You want to remove that effect. That's why you look at it different before and after in experimental, different before and after in control. Then that difference in the two now, you now see is there any difference in the two. That is the difference.
Okay, so what is the place? What's the place of co-founders, confounders? You know, in what we are talking about now. How do you control for the other contextual issues that would have, you know, resulted to the change you are seeing? How do you control for that one and now say that, okay, this change that I'm seeing is solely attributable to what I have done, my experiment or my intervention?
And that's why the people try to, you know, in experimental design, in fact, the design, experimental design, the way they design is to even remove confounder have been issue from the start. So by you doing that, you are trying to remove the effect of confounder. Yes, I mean now. That's why it is observational study that you leave the confounder to analysis. But in experimental, you still do do control, but most of the confounder is control at the design stage for the experimental design. Why in observational, because you cannot manipulate people, because it's difficult to perform experiment with human in some situation. You have to now leave the effect of confounder to when you are analyzing. So sometimes also you can see remove the effect of confounder from the base that you, if you want to know if this confounder is even have effect, in the baseline, you try to look at the factor responsible. That's for the baseline. So to really see the effect of those confounders, if they have effect at the baseline, before you proceed. And when you are not proceeding, you now make sure that all those factors, you factor a lot of things in. So when you are running your analysis, like now, even the last one, the different, whatever what you get, you can see remove the effect of confounder, because when you look at the result, you can try to analyze do logistic regression. That's where we do logistic or linear regression, multiple regression to remove the effect of a confounder. But for experimental design, most of the effect is already removed at the design stage. So there's much that. That's why in this person's work I did now, when we did some course, we didn't see any factor because of the way they have designed it. Right? So if it was to be observational study, all of those things will be coming out. But if you still have, when you do your cross tabulation, you do multiple regression. That's where you remove confounder. That's what we will discuss here.
Are you saying that there is no place for logistic regression in experimental study?
I'm not saying that. But most of the time, it may not even, okay, like for your friend study now, we look at we do chi-square, all those things. There's nothing significant in those factors. There's nothing. And there's a significant difference in that thing between experimental and control, even at the baseline. So, but when we look at the factors, other factors that he put in the studio, you can't find any significant difference. Because it's where you are having many factors involved that you now begin to say, okay, there are a lot of confounders. We did the logistic regression for Duce, but this one there's no need for their own. For Duce also is almost like this, but it's about immunization. So we did the quickly run this one and finish. So you can see that this one is paired. You can see it's parallel now. And that score before cancelling, score after cancelling. Can you see? They're in parallel. I didn't put it. We didn't put this one. I say 1 to 9 and this one because it's the same people. Because when you are talking of, because one thing for you to actually know how to differentiate between this, when you need to arrange in parallel and arrange in series, is this. In your data view, where you are entering your data, each line is each person, each subject. Like for this one now, number 1, maybe it's Eunice. This is the exercise score for Eunice. Since you take this from Eunice before and after, so everything about Eunice must be on this line. So before will be after. What you can do is that, like for your Elima, Eminence, this and that, some of those knowledge, the question you have, you now put pre. The other one, post. You have to differentiate because it's on different column. Post, pre, post, pre, post. Because it's for the same set of people you did the pre and post. You get the picture now. So the pre and post was arranged in parallel. But because they have many 3 groups, the group are arranged in series. Our own group are arranged in series, but the pre and post are arranged in parallel. That's all. So let's run it. So anxiety after is in parallel. Can you see? So you now say analyze. I hope you can see. Compare means pair sample t-test. Can you see? No, now click on it. Can you see the way they arrange it also? So before, after, move it. If we even click on both of them, move it, it will do it like that, put it in the front. So you just say, okay. I don't know if you can see. Let me share the output. Can you see the output now? Can somebody see the output?
Yes, sir.
You see?
Yes,
remember,
sir.
The mean difference was 33.3 we got the other time. Can you see? Look at the mean for individual group, but that's not what it was used to calculate. If you look at the mean for individual group, you can even see, but
yes,
look at it, the mean of the difference is what is here.
right.
This is the standard deviation we calculated. This is different, the mean, this is the standard error rather. This is the confidence interval. This is the T we calculated. This is the degree of freedom. This is the p-value. So it shows it's significant. Look at it. The confidence interval. Does it cross 1 and cross 0?
No.
So
It does not, sir.
You see, can you see? From 50 to 30. If you run it the other way, the way I did the other one, instead of
minus.
Because
minus
if you look at the anxiety before is bigger than after, averagely. So what I first of all put there was anxiety before. Let's put after first. After, anxiety after, then we now put before. So you go to remove after from before, or before from after rather. It will give you, can you see? It's the same thing. Can you see? Now give you from minus to minus, but it's still the same thing. Can you see?
Yes, sir.
So it's the same answer. It's just for you to, if you do like this, you see the answer. All you need to do is just to correct it. Also, okay, the difference is this 33. Those will put minus. But if you want to now swap you have to now if you want to write the confidence interval as plus, you have to solve it. This to be 15.7 to 50.95. So any question? If you look at the interpretation of t-test, it's the same for all the form of t-test. The interpretation and the confidence interval. Though the confidence interval is not part of the TO. It's just like they just there because it's hypothesis test.
Oh, okay, hypothesis.
Yes, it's not part of the T. It's different, but they just incorporated hypothesis testing to the confidence interval and hypothesis testing, the same procedure. So that is the result. If there's a question, I think that's the end of today's show.
Wow, thank you, sir.
Yeah.
Thank you, sir. Sir, I have a question.
What's your question?
It's not with respect to this one. If anytime you report a median, are you supposed to report the interquartile range with it?
Some people that came with that idea, if you are going to, because if you quote the mean, you usually quote standard deviation as the measure of variability. So if that data is skewed, you now decide to quote median. So some people are advocating that you quote interquartile range as the measure of variability also. But I don't usually do that. Some people just give it there. You may do it, you may not do it. But
sorry, sir. In my study, doing my presentation, okay, let me give an example. Like age now, we have the mean, we have the median. What does that mean? And I think the mean was significant.
Okay, the issue there is that
when you do constant,
the mean is different from the median, right? The value. Far different.
Yes.
And what did we use?
Yes.
What statistic did we use to compare?
Which one is preferable?
I think Sasha, you know what she's asking? Is that question? Is that thing I was telling you? That's when you put mean and median at the same time.
You see, the issue there is that if the mean and median are very close, the mean, when something is normally distributed, mean, median, and mode are the same. So when you show, you don't need to show the rest. But if something is skewed, the mean is different from the mean. It's good to show the value of the median also. It gives you a picture that has a skew. So if the mean and median differ significantly, it's good to, if you show the mean, show the median also. But some people are saying that if you show the median, let's know the interquartile range also. Okay, now in your own, which statistic did we use to compare the mean and the age?
It was the age group that showed the mean and the median.
Was it you? That's what he's asking.
Well, yes.
It shows that
the mean was that you was beside it. See?
And the mean should be.
The issue. What was the question they were asking then?
You're asking why would I report mean and median at the same time? Show it on the table that it should just include, write only one, whether it is mean or median. I should not write both together.
Who said that? Who said that?
I think
Who said that?
He was not or Dr. Zazuruki.
I think it's one of them.
I say,
both of them, at the end of the day.
And it's because that's part of the difference. They are half informed. If you can see that the mean and median are different, so what you should, that's the logic now. That's the logic of showing.
And that's what I explained, though. That's what I explained during the presentation. That's what I explained.
Exactly.
But everybody has their opinion.
No, they are half informed now. So they don't. So what should you know? If the mean and median are the same, that's why you usually show the mean to represent the measure of central tendency. But if they are not the same, it shows the skew. If you show the mean, if you show the median, it's good to show both, so that people will have the picture that is skewed. That's what they don't understand. So that you show that.
But it was significant. What does that one? The T was for the mean, Abi.
What?
The T test for
Is it T test of match with you? we use.
It was T that was beside you, T and the P value. Students T test.
Look, let me tell you something. By tomorrow, let me tell you something. By the time we do parametric tomorrow, you will notice that all these things they say that parametric is comparing media. It's only one aspect that even comparing. You see, man within you is not even comparing the media. It's not actually comparing the media. The issue is that when something is skewed, you are comparing the two groups. So for t-test, you use the mean, yes. But for non-parametric, you don't use the mean. It's not even one of them that use the median. It's only even the one that use the median. The median does not even go into calculation. You just use the median to divide the thing to 2. The median is not even used. You are not actually comparing the median. So do you get the picture now? It's only that if it is skewed, the mean will not be appropriate. You cannot compare the mean because it's already skewed. So to compare the two groups, you now use non-parametric. The non-parametric doesn't really mean that it's comparing the median. The median, even most of the non-parametric, the median don't even get into the calculation. So, you know, when people are they don't even know what they are saying. They just know that somebody says something somewhere. They are just talking. So that's just it. So, you know,
I have another question. There was this thing that I was reporting. They were talking about predictors. I got the odds was 0.36. And I now said that the odds of having that sort of was 0.36 more likely than those who had no support.
That's not how to invent.
I think that you say less likely. Eh?
Yes, it should be less.
Because the reference category was people that had no support. The reference category was people that had no support. So I cannot say that people that had support, 0.36 less likely not to have good support. You understand what I'm saying, sir? But they say I must not mention 0.36.
See, listen to me. Whenever you are interpreting, forget about reference. Once the odd ratio is 0.3, is 0 point something, it shows that that particular group is less likely to have that attribute than the reference one. That's what it shows. It doesn't matter. But was it statistically significant or not? So, was it statistically significant?
It was significant.
Which of the?
Yes, sir.
Which one?
Yes, sir. The other source of support, the people that are not in support group, people that are not in support group, the predictors for those who are not in support group, had other source of support.
They had other source.
And it was the odds was 0.36.
Other so okay. Okay, that was what. Listen, that's another thing, sir. That was under no support. The interpretation it doesn't even affect because there are different groups. So let me.
Do I report it?
No, if there's no, I'm coming. If there's no question, let me just pause our this so that we will not come and dilute our video with your this.